How do we calculate a formal charge? Well, a formal charge is equal to the number of valence electrons in an isolated atom. So you pick one of the atoms in the structure and you say, what is the formal charge of this atom? So you say, how many valence electrons does that atom have? So if it was oxygen, it would have 6 valence electrons. And then we subtract the assigned electrons. There's actually a much more complicated formula than this. It says take the valence electrons, subtract all the lone pair electrons and half of the bonding pair electrons attached to it. That sounds really complicated to me. It's a long formula. It doesn't fit nicely on one line. This one, you can say FC is equal to VB minus AE. I like that because it's nice and short. So the assigned electrons are all of the lone pair electrons, because if I had, for example, to whom do, actually, let's make that an S, just so it's something different, okay? To whom does these yellow lone pairs belong? Belong to oxygen. Do they belong to sulfur at all? No. Sulfur owns these green electrons, yes? Who owns the bonding electrons? Both of them. So you kind of split up the bonds and you say, half of this bond goes to sulfur, half of this bond goes to sulfur, half of the top bond goes to oxygen, half of the bottom bond goes to oxygen. If you were to write it, if you were to draw your Lewis structure using dots, right, like this, it would maybe be a little more obvious, right? And, oh, actually, oh, where to go? Let's make these ones red. Okay. So these here are sulfur's assigned electrons. And these here are oxygen's assigned electrons. Yeah? So in this case, the valence electrons for oxygen is 6. The assigned electrons is 6. What would be the formal charge? 0. Okay? And the most stable is when formal charge equals 0. That's why O2 is a really good substance, or if you had oxygen and sulfur, that's why they tend to make OS like that, okay? Because things love to have a formal charge of 0. So basically you count all the lone pairs, and then each bond counts for just 1 electron, because each bond contains 2 electrons, but one belongs to atom A and one belongs to atom B. So the easiest way to count assigned electrons is to count every dot and every line. Every dot counts for 1, every line counts for 1. Yeah? Each dot, count 1. Each line, count 1. So here's formaldehyde. Oxygen has 6 valence electrons because it is in group 16. Once again, we have 1, 2, 3, 4 dots, and we have 1, 2 lines. So that is 6 assigned electrons in total. So we have 6 minus 6 is 0. How about carbon? Carbon has 4 valence electrons. To isolate carbon, you can kind of maybe, if you want to in your head, draw a circle around it, or you can even literally draw a circle around it. But how many lines are attached to carbon? 4. Oh, guess what? 4 lines. There's no dots. So 4 minus 4 is 0. Hydrogen. One has 1 valence electron. It's got 1 line attached to it. So 1 minus 1 is 0. This is a nice stable structure. Everybody has a formal charge of 0. If you want to write the formal charge on an atom, you write it beside that atom and put it in a little circle. Okay, so carbon, these are our formal charges here and here. How about you cover up, get yourself a piece of paper so you can cover up the stuff over on the right. Okay, or put your binder over it or your pencil case or something. Okay, cover up the right-hand side of the page with something or other. And figure out the formal charge for carbon and nitrogen in CN. Oh, that's a boring one too, isn't it? Pardon me? Oh, carbon has 5. What am I doing? I'm so silly. Because it's got 1, 2, 3, 4, 5. There we go. So that is -1. Yes. And it's not surprising that we have a charge of -1 here and a 0 because the overall charge is negative. Okay? Normally a compound will sum up to 0. Everything in the compound will add up to 0. But if you have an ion, it will add up to the charge of the ion. Okay? So they add up to 0 for neutral compounds. And they add up to the charge for an ion. Is good? Okay. So basically, if you're given 2 structures and you're like, which one's better? You find the formal charges on everybody in there and you say, can I find a structure where they are all 0? If I can find a structure where everybody has a 0, that's the best. Okay? If I can't find a structure where everybody's 0, let's say I gave you a choice, not in this one because there's no other choice, okay? There's nowhere else I can put electrons in any other situation. But let's just say we had a situation where I could either have oxygen -1 and I don't know, hydrogen, no, not hydrogen, hydrogen's a bad example, carbon 0, or I could have oxygen 0 and carbon -1. Which of these 2 would be the better choice? Can you make an educated guess based on what you know about atomic properties? Top one, why?
Then, it's just like valence electrons minus the assigned electrons. Oxygen obviously has more valence electrons.
It does. Plus, oxygen is further right on the periodic table, which makes it more electronegative. Therefore, the first one is more stable. Yeah. So if you have to put a negative charge on something, put it on the most electronegative. Yes? Is good? Okay. You can also think about, sometimes you can just do it by doing a quick look rather than doing the valence electrons minus the assigned electrons. You can think, what does carbon normally have? Carbon normally has 4 bonds, right? That's normal carbon. Normal substances have a 0 formal charge, okay? Formal charge equals 0. In our cyanide ion, we have 1, 2, 3. Oh, we got more. Yes, we have 1 more. So we have 1 extra electron. That one there. Compared to this one here. And that tells us that we have a formal charge of -1. So if you prefer to think about it that way, you can. Okay? Nitrogen normally has a lone pair and 3 bonds. That's normal nitrogen. And in our structure, in our CN, nitrogen has 3 bonds and a lone pair. So it's the same, so its formal charge will be 0.
Yeah.
If that makes no sense to you, just keep doing valence electrons minus assigned electrons, okay? This is just kind of a more intuitive way of doing it, okay? Most stable, all the charges equal 0. If that's not possible, it's going to be the one with the smallest formal charges. So if you can get down to +1s and -1s instead of +2s and -2s, that's better. Yes? +1 is better than +2. And you want the negative charge to be on the most electronegative element. So here we have N2O, and there are a whole ton of structures here, I think. Find the formal charges on all the atoms, and then choose the most favorable, stable Lewis structure. And you can always, if you're wanting to do the calculation, you can notice that the n on the left is the same as the n on the right, so you only have to do the calculation once for that one. Oh, I keep writing valence electrons. I mean assigned electrons. There we go. Assigned electrons. And notice if you have found the formal charge of this nitrogen, you'll also know the formal charge of this nitrogen because they are the same. They both have 3 bonds and 1 lone pair, so you don't have to calculate it twice. Okay, you can just say, oh, I already did that one. Okay. You would normally not have this many structures to work on, okay? I just wanted to give you like a, what do you call it, crash course. Ooh. I keep saying valence electrons minus valence electrons. I am so sorry. Valence minus assigned. And then when I correct it, I write AA instead of AE. I don't know. Something wrong with me today.
Oh, that's what you know, I wait, that's what you're right. I've been ready to
So which structures can we get rid of immediately because they've got formal charges of 2 in them? We can get rid of A because it's got a +2. We can get rid of B because it's got a +2 and a -2. That doesn't look good. Let's see if we have any other 2s. No, we do not. Oh, yes, we do. D has a 2 also. So we'll get rid of D. So now we are down to, and I'm going to put my -1 down here so I can see it a little bit better. We are now comparing do we want the 0 to be on oxygen, or do we want the 0 to be on nitrogen? Do we want the -1 to be on oxygen, or do we want the -1 to be on nitrogen? Who is more electronegative? Oxygen. So our best structure is C. How do we feel about that? Okay? All right. There's an answer on the next page. I mean, it's all there for you if you want to. And then there's some exercises, which we're not going to do right now. We're going to move on to 11.3C on page 84.
Yeah, that's why it says plus.
Okay, lattice energy has to do with crystal lattices, and crystal lattices have a lot to do with ionic compounds. So a lattice energy is a measure of the ionic bond strength. Okay? So the lattice energy tells us about the ionic bond strength. And we have a little warning here. Make sure you just pay attention to which type is being used. You can either say, how much energy does it take to break that bond? That's going to be positive. Or you can say how much energy is going to be released when that bond is formed. That's going to be negative because you've got endothermic and exothermic. So lattice dissociation enthalpy, the values are highly endothermic. This is bond breaking. You have to put a lot of energy into it. So we take our solid crystal lattice and we turn it into Na plus and Cl minus gaseous. Notice that it goes to, it's how much does it take to completely separate them? And if they're completely separated from one another, what state do they have to be? Gas. Okay, so this would be plus lattice energy. Now, if instead we have lattice formation, that's where we start with Na and Cl gas, Na plus and Cl minus gas, and we get the solid. So we start with gas, ion, gaseous, ion, and we finish with the solid, and then we would have our lattice energy over on the right-hand side. And remember, when the energy is on the right-hand side, delta H is negative.
So it's
Exothermic. Because this is bond formation. So really, most of the time it's not going to matter what the sign is because you're going to be given lattice energies for a few different substances and you'll have to compare them. And they'll either all be negative or they'll all be positive, and it's just the magnitude that matters, not the sign, okay? So when you're comparing lattice energies, you're really just comparing the magnitude. It doesn't matter whether you call it positive or whether you call it negative, okay? All right, so we remember again, we have Coulomb's law, KQQ over R squared. So two factors increase Coulomb's law. One is having high charge and one is having small size. So if you have a substance that's forming with, like, let's say we just had NaF compared with Na2O compared with Na3N, which of those would have the highest lattice energy? Whoops. Which of those three? Yeah, the last one, Na3N, because N has a larger charge. Yeah, I think so. Yeah, but no. Okay, so Q equals 3. Now, when you have ions in a row, the sizes are different. Like fluorine would be smaller than oxygen and nitrogen would be bigger, but those sizes are not dramatically different from each other, not like when you go down a row. Okay, when you go down, or sorry, down a column, when you go down a column, you add a shell. So it is dramatically bigger. As you go across a row, they get smaller, but each step is not dramatically small. Does that make sense? So charge, if you have a difference in charge, go with that first. Yeah? But if you're comparing, you know, say we had KF, NAF, and LIF, then in this case, because they're all +1, it's going to be the size that matters. Okay? We have the smallest R, therefore the highest Coulombic attraction, therefore the greatest lattice energy. You probably didn't even need me to teach you this. You probably, if I gave you enough time, could just sit there and kind of think it through, right? But we're going to kind of move things along. So the greater the charge, the stronger the electrostatic attraction. The smaller the ionic radius, the shorter the distance, the stronger the electrostatic attraction. Okay, and you can see here we have lattice enthalpies get smaller as we go that way. Is good? Okay. Now, usually you'll be given lovely, obvious choices, okay? You'll be given like MgO compared with NaCl, yes? And you'll be like, oh, look, these ones are smaller and they have a bigger charge. These ones are bigger and they have a smaller charge. Yay, which one has the greater lattice energy? This one has the greater lattice energy, yeah? So if you could please try the little example question on page 86 and then check with your partner. Yes. My papers were in this grade right now. Okay, what'd you guys get for A? NaCl or KCl? Which one? Everybody, which one? NaCl. How about B? NaF or NaCl? NaF, why? F is smaller. And for this one, Na is smaller than K. MgCl2 or NaCl? MgCl2, why? Mg is 2 plus, Na only 1 plus. MgO or MgCl2? MgO, why? O is smaller. and it has a larger charge. I would go with the smaller because I always get a little confused about whether the Cl2s, they do have 2 minus when you put them together. Do you know what I mean? However, because there's 2 of them, they take up a lot of space, and then it's kind of separate. So I would just, if I had to explain it, usually their explanations on AP, they only want 1 mark's worth of something. And if you say O is smaller, you're done, right? You've given your 1 mark's worth of whatever, okay? Okay, so the relationship between lattice energies and physical properties, these are going to also be applicable for when we get into intermolecular forces. So the relationship between lattice energy and physical properties, 1, melting point. The higher the lattice energy, the melting point. Tell your partner. Higher. Does that make sense? Because if the bonds are stronger, yeah. Stronger bonds require more energy to break. They require more energy to break, and remember that temperature is a measure of the average. Temperature is a measure of the average. Kinetic energy. So if you want more energy, you heat up your particles, you give them a higher temperature. Yeah? So that's why melting point is higher, because you need a higher temperature, which gives you more energy to overcome that stronger lattice energy, that greater lattice energy. So our sodium halides, that means sodium combined with your halogens, so sodium fluoride, sodium chloride, sodium bromide, sodium iodide, you'll notice as we go from smaller to larger, yeah, lattice energy, lattice energy, as we go this way, lattice energy is increasing or decreasing? Decreasing. And our melting point decreases. Is good? Okay. You're going to see trends like that in intermolecular forces. So if you have stronger intermolecular forces, the melting point will be higher. If you have weaker intermolecular forces, the melting point will be lower. It's the same principle. It's just instead of dealing with ionic bonds, you would later on be dealing with intermolecular forces. Okay, so if you have something with hydrogen bonds, which are one of the stronger kind, it's going to have a higher melting point usually than something that has only London dispersion forces, which are fairly weak.
Say lattice energy is directly proportional to melting point.
I would say melting point is directly proportional to lattice energy.
It's because lattice energy affects melting.
Lattice energy affects the melting point. And then instead of having a graph here, we have our group 2 oxides. So we have magnesium, calcium, strontium, barium, and we're pairing them up with oxygen. And the same thing happens. Our lattice energy decreases. And the melting point also decreases. And that's as the ions are getting bigger. And then there's a bunch of stuff here. Magnesium oxide is used to line furnaces. Why? Because it's got a really high melting point, because it has a really high lattice energy. Which of these four do you think would be the easiest to dissolve? Out of these four, which would be the easiest to dissolve? Probably barium oxide, yeah? Whichever one has the lowest lattice energy is going to be the easiest to dissolve, because you've got to break less strong forces. Okay, and I think, are we getting onto here? Hardness. Hardness is resistance to scratching or abrasion. Again, the higher the lattice energy, the greater the hardness. So magnesium oxide is harder than sodium fluoride. This has higher charges, therefore higher lattice energy. And the sizes are relatively comparable. They're not that far off of each other. Now, I'd actually like to stop there for today. Your homework is going to be 11.2F. But I'm also going to give you today some review material, so you can start working on it. If all you can do today, if you've only got time for 11.2F, hey, you've got weekend to work on the review stuff, but I thought I'd give it to you today. So let's put it out. Where did I put it? It is here. Oh, okay. So we have free response questions and the free response key. The multiple choice questions are on the little back table there. Okay, so you can find the bonding MCQ on the back table. I will also post it on Teams. Yes. Yes. I meant to do that this morning and then I forgot. I was thinking of you and then I was like, oh no, I've got a grade 9 quiz I need tomorrow. So I did that instead. The blood bath?